Hello everyone. So in this lecture, we will see example of a variable volume batch reactor and another example of semi-batch reactor. I am specifically choosing these two examples. Good questions. These two are good questions. I found considered it as because normally CSTR, PFR, or any other reactors are mostly found, but batch reactor having variable volume is very. Those questions are very selectively taught and not many examples are there. So I am taking one problem from H.S. Scott Fogler textbook, and this problem states that consider cylindrical batch reactor that has one end fitted with frictionless piston attached to a spring. The reaction is given by this. The rate law is also given by this. Is taking place in this type of reactor, and so this is the reactor where this is the volume of the reactor where the reaction is taking place. This is head cover, and this is the spring. And in this question, they have asked write the rate law as a function of conversion, numerically evaluating all possible symbols. Answer is given. And B question, what is the conversion and rate of reaction when the volume is zero point 0.2 feet cube? The answer is also given. Some additional information are also given. The equal moles, that is equimolar, are present in the feed at time t is equal to 0. Initial volume K1, spring constant. Okay, the K1 is the reaction rate constant. The spring constant is such that volume and pressure of the reactor is related like this. So, and V must be in feet cube and P must be in atmosphere. So, in this problem, we can see two things that the rate volume will expand, spring will come try to uh, block that expansion. So after equilibrium, the volume and the pressure inside the system will be like related like this, because the volume, if the gas tries to expand, spring will try to stop that expansion effect and come to an equilibrium volume. So volume and pressure will be related like this. Also, we will assume the gas is ideal gas, so we will get another relation relating ideal gas. And another thing, we are seeing that the units chosen here are been fit, feet, pound system. So British system they have chosen. But another thing is good that they have written all the things in British system also, like gas constant. They have written in British system, FPS system. Okay. Now to solve this, the rate of the reaction given here is A plus B gives 8 times C, 8C. And volume and pressure are related like this. So B is equals to alpha P. I am writing alpha. Suppose alpha is equals to zero point 0.1. Not suppose alpha is zero point 0.1. I am writing with notation symbol, and I will retain the notations in the while solving the problem and finally evaluate the values of each notation. Now V is equals to alpha P. Also, as said, the gas behaves ideally. So we have pressure volume is equals to nRT. And initially, suppose P is P naught, V is V naught, N is N naught, and R is R, whatever it is constant. And temperature also in this problem they have considered it constant. So T. So the N is total moles. N is total moles and N naught is total initial moles. Total initial moles will be twice of any one of the moles present because equal moles. Now, if we divide these two expressions, then we get PV by P naught V naught is equals to N by N naught. Here pressure will change. The pressure is not constant. Now V is equals to alpha P. We can substitute P is equals to V by alpha. Here in this expression, if we substitute, we will get P is equals to V by V naught. Alpha alpha will get cancelled. Whole square is equals to N by N naught. Now, right, let me write it properly. V by V naught whole square is equals to N by N naught. Now N by N naught from stoichiometry we know that it is equals to 1 plus epsilon A conversion of A. Now in this problem epsilon A is change in stoichiometry quotient 8 minus 1 minus 1. So 8 minus 1 minus 1. 8 minus 1 divided by stoichiometric coefficient of A. The limiting reactant will be A or B, either we can choose. I am choosing A because equal initial modes are present and both are stoichiometric coefficient have 1. So stoichiometric coefficient of A is 1, so 1 into the mole fraction of A. The mole fraction will be half because equal moles are present means initial mole fraction is half. So the value is 3. So epsilon A is 3. So, so volume by volumetric flow rate is equals to root over of 1 plus 3xa. Now, to write the rate expression, rate, they have asked the rate law. So the rate law is given by minus Ra is equals to K1 Cs, okay, so K1 Cs square into Cb. So Cs square into Cb. So K1 concentration of A is Na by volume whole square into Nb by volume. Now equal moles are present. Suppose Na naught, Nb naught moles are present. Now it is said that Na naught is equal to Nb naught. Equal moles are present. So at after time t, at t is equals to 0, and even after t is equals to t, Na naught minus beta, Nb naught minus beta, and here C will be formed 8 beta. This Na and Nb will be equal. Na is equals to Nb because these two quantities, these and these are equal. So let me write this as Na, Nb as Na, K1 Na cube divided by V cube divided by V cube. It means concentrations will also be equal, which is equals to K1 V cube, this is cube, means 3. K1 Na, in terms of conversion, Na will be Na naught 1 minus conversion of A whole cube divided by volume is given by this volume naught root over of 1 plus 3xa. So volume naught cube to 1 plus 3xa to the power 3 is 1 plus 3xa to the power 3 by 2. So we get the final value K1 Na naught by V naught whole cube to 1 minus xa cube divided by 1 plus 3xa whole to the power 3 by 2. This is 3. This is 3 by 2. 3 by 2. Now the answer is given to the problem. We get the conversion term, function of conversion term correct. 1 minus x whole cube divided by 1 plus 3x whole to the power 3 by 2. Now you will get the numerical value which is evaluation of this quantity. Now Na naught by V naught. Now in this question, this initial values are P V naught is equals to N naught R T. This is the expression we have used. Initial value, initial case, initial condition, not case, initial case condition. Now initial volume is given, so I will replace the P naught with volume, and it is equals to V naught square by alpha is equals to N naught R T. So initial total moles is equals to V naught square by alpha R T. We have used V naught, sorry, we have used V naught is equals to alpha P naught. This relation, the spring relation. So this is the expression now. The volume V naught is given as 0.15 feet cube. So we will put this value volume 0.15 feet cube square divided by alpha. I have chosen. I have said. I mean this is zero point 0.1. So rank R value is 0.73 0.73. Now, see one thing, this is 0.73 in degree Rankine, but temperature is in degree Fahrenheit, so you need to convert it to degree Rankine. Now, in generally, if it is in exam, the conversion, how it is converted from Fahrenheit to Rankine is given. If you convert 140 degree Fahrenheit to Rankine, it will come 599.67. So I will put the value 599.67. Now, if you solve this, you will get 0.15 square divided by zero point 0.1 times 0.73 times 599.67. You will get point 1234, 5.138 into 10 to the power 13, 5.1398, sorry, 5.1398 into 10 to the power minus 5. 1, 2, 3, 4. Sorry, 10 to the power minus 4. 10 to the power minus 4. Okay. Now, n a naught is equals to n naught, sorry, n naught, n naught by 2, which is equals to this value divided by 2, which is equals to this one, 0.0000. 1, 2, 3, 4. Okay. So this is 1, 2, 3, 4. 2.5699 into 10 to the power minus 4. So this is the value. Now, so we will evaluate this value. K1 in a naught by volume naught whole cube. K1, K1 is given by 1. Initial volume is 0.15. So 1 times the 2.5699 into 10 to the power minus 4 divided by initial volume 0.15 feet, this whole cube. So we will evaluate. So this divided by 0.15, we will get this, and then whole cube is 5 point, sorry, 5.0289 into 10 to the power minus 9. This is we get 5.0289 10 to the power minus 9. So answer is, yeah, 5.028 means 5.010. So we got the first question done. So rate expression is this 5.0289 into 10 to the power minus 9. 1 minus xa is whole cube and 1 plus 3xa whole to the power 3 by 2. Now to proceed with the second question, what is the conversion and rate of reaction when V is this much, 0.2 feet cube? Now we will use this expression for related conversion. They have asked conversion. So V for B part, V is equals to V naught square root 1 plus Bxa. Now Xa is equals to B by V naught square B by V naught, sorry, V by V naught square minus 1, this is 3. So conversion of A is 1/3 of V by V naught whole square minus 1. So 1/3 into zero point 0.2 by 0.15 square minus 1. If you evaluate this value, zero point 0.2 by 0.15, this value squared minus 1 divided by 3. We get to 0.259259. This is the value. And if we check with this conversion, so this is correct. And if you put the x value in that expression, in this expression, we will get the minus, sorry, RA expression. Okay, but if you want, but suppose if you want to evaluate how this is conversion is varying at the time, then you have to write a rate expression carefully. This is the rate expression. So to write the rate expression, you will have to use expression like inlet is zero, mole balance in the gas in the steam batch reactor system, inlet is zero plus RA into V is equals to dNA by dt. So you have to use this value of RA here and V as this value. So the differential equation and Na will be Na naught 1 minus Xa. So if you write the differential equation of the governing system, I am writing the RA expression as this form. This is K, this is a better form. So RA is minus K1 Na naught by V naught whole cube 1 minus Xa whole cube divided by 1 plus 3Xa 3 by 2 into volume is V naught root over of 1 plus 3Xa is equals to Na is this value Na, so minus Na naught dxa dt. So if you simplify this, Na naught will 1 cancel, V naught will 1 cancel, so it will remain as Na naught by V naught whole square. This 3 by 2 minus 1 by 2, if you simplify the powers of 3 by 2 minus 1 by 2, this will be 1 minus xa divided by 1 plus 3xa, sorry, 1 minus xa cube divided by 3, 1 plus 3xa is equals to minus, this minus minus will get cancelled, this will become plus, or best to remove it, dxa dt. So this will be the differential equation. So this is the differential equation governing the system. You can integrate it by hand also. It seems like you are very good at integral calculus. You can write this equation and solve this x as a function of t, or else you can solve it numerically to some ODE solver like in MATLAB ODE 4.5. Now we will see another example of this is an example of semi-batch reactor. So this is an example of semi-batch reactor. This question I have taken random from internet. So it says that a catalytic reaction takes place in the liquid phase in an isothermal semi-batch reactor A to C. This is the rate expression with K being this value. Now initially the reactor contains 2700 liter of solution whose concentration is A 20 mole per liter. So it is given that initial concentration at T is equals to 0. I will be writing SCA naught is equal to 20 mole per liter. Initial volume V naught is given 2700 liters. Okay, the concentration of B. Okay, B is the catalyst. Concentration of catalyst B in the reactor is 0. So CB at T is equal to 0 is equal to 0. Now, that means no moles of B is present inside the initially, and at T is a constant solution containing 0.05 mole per liter of B is fed to the reactor. So CB feed is 0.05 mole per liter. This notation is feed with the volumetric flow rate is Q is equal to 12.5 liter per minute. How many moles of product C are formed after 200 minutes? Write the equations required along with the initial and final values to solve this problem with polymath. So I will be not using polymath. This problem does not require actually any solver. I will show how to solve this. Now, to solve this, a semi-batch reactor principle is this: a batch reactor. This is a liquid phase reaction and no gas generation is there. So volume or pressure we will not care much. So this is a stirrer, and this is the volumetric flow Q and CB feed to the reactor, catalyst catalyst fed to the reactor. And we will assume one thing, that the density of this liquid and this liquid, the fed liquid and this liquid in the reactor are same. So that if you do the mass balance or the volume, how the volume change, we can directly write it like this: dv dt is equals to q. dv dt is equals to q. Suppose if if the this density and this density are different, then the mass balance will be like this: d rho in the tank into v divided by dt is equal to rho feed into q. This will be the actual mass balance, but I will be assuming the density in the tank and density in the feed are same, because this is a liquid phase. If you consider density variation, then many other parameters are also required. In most cases, liquid phase densities in the reacting system are all near same, because sudden density change will create issues. So density tank is equal to density feed. This is actually mass balance equation. So if these two are equal, then the volume inside the tank can be represented as V is equal to V naught plus QT. This I have integrated between V naught to volume T. V naught is initial volume, T is the time. So this is the expression. Now let us do the balance of A. A balance. A balance. No A is entering in the system, so 0 plus RAV is the generation of A is equals to accumulation of A in the system. So this is the A balance. Now, if we evaluate the expression RA is given as K minus KCA into CB, CA into CB into volume is equals to dNA by dt. Now, if you change CA as NA by V into NB by V into V is equal to dNA by dt. Where one volume is getting cancelled, so I get expression minus K NA NB by V is equal to dNA by dt. Okay. Now, in variation of NB in this reactor volume is needed. Now, to get the variation of B, we will do B balance, that is catalyst balance. Now, to do B balance, there is the volumetric flow rate QCBF is entering in the system. No in generation or consumption of B, and this is the accumulation of B. Now, if you integrate this, as in the question, it is mentioned that there is no B present in the system at t is equal to 0. So, no moles of B present in the system. If you integrate it, we directly get NB as a function of type QCB feed into T. So, we get differential equation. We will put this value here. So, finally, we get minus KNA. NB is QCBS T divided by volume is V naught plus QT is equals to dNA by dt. So we get a differential equation between Na and T. Now this differential equation does not need any polymath or any software. This is a simple straightforward differential equation, and I will show and rearrange this a bit. dNA by Na is equals to minus k q CBF t divided by V naught plus q t into dt. Now, if I can divide it by q, q CB f divided by q, t by, sorry, no need to divide by q. I can easily I can easily write in terms of partial fraction, PV out, QT plus volume. I can arrange the partial fraction if you know QT plus V naught minus V naught divided by V naught plus QT to DT. So this will be equal to minus KCBF, which is F 1 minus V naught by V naught plus Q into T dt. Now let let me now if you do the integration, suppose if you do the integration between n a naught, which is initially present in the system, to n a t, which will be the final dna by na is equal to integral of 0 to t, which is initially time t k c b speed 1 minus v naught by v naught plus q t into dt. Now, if you evaluate this expression, you will get natural log na divided by na naught is equals to minus kcb speed time minus v naught will come out of the integration with q to, in v naught will come out of the integration, so v naught will be again multiplied by q to get sorry, v naught will be divided by q, v naught 1 by q to get this fraction q t term. So you will get natural log at t v naught plus q t divided by v naught. So this is the expression we will get. Now let me define a dimensionless, a time unit kind of thing. V naught by q has a dimension of time. This will make expression a bit simpler. Q C B F t minus tau natural log t minus tau natural log 1 plus t by tau. This is the expression. Now if you break this expression, Q C B F t plus k C B F tau ln 1 plus t by tau. Now if you take anti-log or reverse this expression, you will get na naught. This is for this term. This is natural log. This can go to exponent 1 plus t by tau. This is t. This is time t by tau k c b t tau into e to this term is e to the power minus k c b s t. So this is the variation of Na with time. Now to get the concentration of C. Now if you see the reaction A to C, the reaction is A to C. So we will write directly A to C. Initially, if this is Na naught is present, 0 moles of C is present. Finally, Na naught minus beta. This will be beta. So we get a relation that Na, this is Na and this is Nc. Na plus Nc is equal to Na naught. So this is the expression. So Nc as a function of time, Nc as a function of time is equal to Nc as a function of time is equal to Na naught minus Na function of time which is equal to Na is given as by this. Na naught will be taken common. Na naught 1 minus 1 plus T by tau KCBF tau e to the power minus KCBF into time t. So this is the expression at time t relating NC and this. So NC is this and Na naught is PA naught into V naught. I am writing this expression in terms of the variables given in question. PA naught into V naught 1 minus 1 plus T by tau KCBF into tau minus e to the power minus K. Sorry, this is not minus, this is product. This is with product multiplied by e to the power minus K CBF into T. So this is the expression. Now the question says, the question has a value. We will solve this. We will find the answer after 200 minutes. V naught these are given. Now tau naught we have defined as V naught by Q. So the initial volume 2700 liter by Q is 12.5 liter per minute. 12.5 liter per minute. It will be minutes in it. Now to solve this 2700 by 12.5 equal to 216 is 216 minutes. It is 216 minutes. So and also we have variable KCBF, KCBF tau. So KCBF solve the value is KCBF is the K value is given as 0.25 and CBF is 0.05. I will solve here KCBF. Here K is 0.25 into CBF. The paid to the reactor is 0.05. 0.05 is equal to 0.0125 KCBF and KCBF into tau is given by 0.0125 2.7. So KCBF tau is 2.7. Now we will substitute all these variables values here in this expression. The initial so KCBF we got as 0.0125. KCBF tau we got 2.7. Tau as 216 minutes. And in this question they have asked t is equals to 200 minutes. We will put this value. Let's see KCBF is point zero 125 into 200 is equals to this. This is minus second exponential. This is this value time 1 1 plus the 1 plus t by tau 200 by 216 to the power KCBF tau is 2.7 this value minus plus 1 times Ca naught initial concentration Ca naught is given by Ca naught 20 mole per liter and volume 2700. The product of these two times 20 mole per liter times the size 2700. So this is the answer. So after 200 minutes, the moles will be 27987.36 moles after 200 minutes. Sorry, moles. Moles are at t is equal to 200 minutes. So we got the final answer that at t is equal to 200 minutes, the answer, the moles will be 27,987. So in this case, we do not require any polymath, but polymath may be required if you write the differential equations in terms of concentration. If you write the differential equations in terms of concentration, the expression will become tedious. Minus k CaCb volume is equal to dNA dCAV by dt, which is equals to V dCA dt plus Ca into dV dt is volumetric flow rate Q. So, and the Cv, concentration Cv, for Cv case also, if you write this in terms of Cv, this differential equation in terms of concentration, this will become QCbF is equals to dCb into V by dt is equals to V dCb dt plus Q into Cb. So V dCb dt is equals to QCbF minus Cb. So this is the volume differential equation where volume is function of T. So if you write the differential equation in terms of concentration, it will become V. Let me divide with V. dCA dt is equals to minus KCA CBV minus CAQ divided by V. This is equals to minus CA is taken common minus CA minus CA KCB plus KCB plus Q by V, and another differential equation is Q by V dCB by dt is equals to Q by V CBF minus CB. So you have to solve these two differential equations with initial condition, that's no concentration of B and B is zero, initial concentration of A is given, volume is a function of time, V is V naught plus QT. We have to solve this differential equation, and solving this coupled differential equation, you need solver. It cannot be done in hand. But the approach I have used, there is no need of solving no need of any solver. So in semi-batch reactor or in any unsteady state, I generally prefer to write the differential equations in terms of moles, because this gives you expression much simpler, not expression, these expression coupled form. But this expression can be solved in one equation. So if you, in most cases, try to write the expression in terms of moles differential equation, but also while writing this, the differential equation may get complicated and cannot be solved in hand. But in most cases, it can be. So, and this solution of differential equation is solved in another YouTube video, which I will mention in the description. So you can check how they have solved this coupled differential equation in polymer. So this is this is what is this is how you should approach a problem in variable volume or in semi-batch reactors.